Good evening, all. Welcome to week 9 of live session from Human Thermodynamics. Today we will be discussing more of the problems related to further problems related to the Carnot engine cycle that we have discussed in the last week. And then this time we will see not just cycles, we will see a combination of two cycles, how you combine a Carnot cycle with a reverse Carnot cycle, and then in different ways of in which you can combine these two things. Most of the problems will deal with that. And then finally we will conclude with, we'll also try to include Closures inequality in this week's discussion. We'll wait for a couple of minutes to let people join and then we'll get started. Hi, good evening. Yeah, hope my screen is visible. So we'll get started. So the first problem, we have two different sources. So essentially we have two different heat engines. In the first case, you have source 1, which can supply energy at a rate of 12,000 kilojoule per minute at 320 Celsius. And in the second scenario, you have another source 2, which can supply energy at a rate of 1.2 lakh kilojoule per minute at 70 Celsius. Which of these sources, one or two, would you choose to supply energy to an ideal reversible heat engine, that is to produce a large amount of power if the temperature of the surroundings is 35 Celsius? So here we have two different Carnot cycles. The sink temperature or the cold reservoir temperature is 35 Celsius for both of them, but the hot reservoir temperature is different, and the heat supplied to the source is also different. Now we need to select one of these cycles such that maximum power is generated, without maximum work can be produced out of the heat engine. So how do you proceed with it? Well, we just start with writing down the information given in the problem. So always convert temperature to Kelvin. Let us say this is the sink temperature T0 as 35 Celsius. So we convert it to Kelvin. Similarly, the source temperature 1 and the source temperature for the second one is also given. With these temperatures given, can you calculate the Carnot efficiency? First, we can calculate the Carnot efficiency, and since the supply is given, we can calculate the work done from the Carnot efficiency. The efficiency is defined as your net work done by heat supply. So Q1 is given as 12,000 kilojoule per minute, and Q2 is given as, so what is the Carnot efficiency for the first case? 1 minus sink temperature by source temperature for the first case. In this case, it will be the sink temperature is 35 Celsius, that is 308 Kelvin, divided by the source temperature is 320 Celsius. If you convert that into Kelvin, that is 593 Kelvin. That gives me an efficiency of around 0.4806. Now, if you follow the same process, what will be the for the second case? 1 minus sink temperature. Now you have some question. You have some question? So if not, you can, yeah. Okay. Yes, this is a Carnot efficiency. Therefore, we have two different sources at two different temperatures. So for the first source, the sink is the same for both the Carnot engines. So for the first one, it will be 1 minus T0 by T1. And similarly, for the second one also, it will be the same. The only difference is with respect to the source temperature. So previously, in the first case, source is 593 Kelvin. In the second one, it is 343. We have the Carnot efficiency and we have Q also. Now I need to calculate the net work done from the heat engine. So that is straightforward. Eta times Q will give you work done. Now, as per the question, which of these two sources would you choose? One or two? One has higher efficiency, but the work done is less. Two has a lower efficiency, but the work done is higher. So, as per the question, which one would you choose? Two, because it is clear that it shows that whichever has a large amount of power is the one that we have to choose. Yes. Okay. Q1 minus Q2 is when you have, say, for example, you have a Carnot cycle. So, let's say this is T1. If Q1 is from this particular source and Q2 is the amount of heat that is being rejected to this one, then the work done will be Q1 minus Q2. But in this problem, what I was asking, Q1 and Q2 are with respect to two different sources. If this is the case, then work done is Q1 minus Q2. If you have a heat engine here, then that will be Q1 minus Q2. But in our problem, 1 refers to a heat engine 1 and 2 refers to heat engine 2. These are two different heat engines. You can calculate Q2 also, but how do you, if you were to calculate Q2, how do you calculate Q2? Like the heat rejected to the sink for reservoir 1. You again use the law that net entropy should be 0 because it's a reversible cycle. So that will give you Q1 by T1 is Q1. I would call it sink, or let's say yes, or let's say rejected by T1. So use this relation where Q1 is this 12,000 kilojoule per minute, T1 is the 593 Kelvin, Q1R is the heat rejected, and T1R is your sink temperature, that is 35 Celsius. If you use it, you can get Q1R, and once you get Q1R, you can subtract Q1 minus Q1R, and that should give you the work done. Anyway, whichever way you prefer. Okay. So if it is clear, we'll move on to the next problem. The next one is a combination of two different cycles. So you have a heat engine operating between two reservoirs at 700 Celsius and 50 Celsius. And whatever is the work output from the heat engine, you are using that work partially to power a refrigerator, which operates again between the 50 degrees Celsius reservoir, the same as the heat engine one, and a minus 25 Celsius reservoir. The heat transfer to the engine is 2500 kilojoule, and the net work output of the combined engine refrigerator plant is 400 kilojoule, which means that partially the amount of work that is generated from the heat engine is used to drive the reversible refrigerator, and the remaining amount of work is 400 kilojoules. Now there are two questions. The first one asks you determine the net heat transfer to the reservoir at 50 degrees Celsius. So just to put it on a schematic, so this is how it is. You have a heat engine, and then this is just to show that it's a reverse one. So basically it's a refrigerator, reverse of heat engine. So Q1 is given 2500 kilojoule. Q2 is rejected the sink. This is the sink, common sink, and this is a refrigerator. So partially this W1 goes to 400 kilojoules, and the remaining is used to power up this refrigerator. So it takes heat from the refrigeration space and goes on. So we are required to find the net heat transfer to the reservoir, that is Q2 plus Q3. So maybe you can take a couple of minutes and then tell me the value of Q2 plus Q3. You can solve it yourself in the meantime. I'll just note down the information. Okay, with this information given, so what is the value of Q2? The first one tells that determine the net. First one you assume a reversible process, so eta will be equal to eta max. So if eta equal to eta max, if it is a reversible process, then we can directly calculate the W1 as whatever eta that we have times the net heat supplied. So in this case, eta is 0.668 times the net heat supplied is 2500. So we have the work done. W1 is known. Now in order to calculate Q3, we need to know. Now we need to know Q3. We know the COP. So how is COP defined? COP is your output. Output in this case is Q4 divided by your input is the work done. You can write this as Q4 can be written as, if you apply the first law here, Q4 is W2 plus Q3. How do you calculate W2? We use the relation W2 as W1 minus 400. Now we have W2, so you can use a COP relation to calculate Q3, like use this relation, substitute COP equal to 3.306, and from there you can calculate Q3. What's the value of Q3 you're getting? You do the substitution. Or to put it here, we can put Q4. Now we have both Q2 and Q3, so you can directly calculate Q2 plus Q3. I think I missed out the Q2 calculation. So once we have W1, you can calculate Q2 here as Q1 minus W1. Q1 is 2500 minus 67. This is for case of a reversible one. So this is straightforward. Now let's say if it is an irreversible case, if both of them are operating at 45%, so what would happen then is your eta will be equal to 45% of whatever is your original eta. So originally it is 0.668. So this is a present eta, and similarly the current COP will be 45% of what is COP previous one. Once you have both eta and COP, you can do the same calculation again. So I'm not repeating the calculation, so it is straightforward. So you just repeat the previous steps, just that eta will be replaced with zero 0.3 and then COP will be replaced with 1.48. So you can calculate and let me know the answer. So what is the value of Q2 you are getting? Q4, Q3, finally Q2 plus Q3. This is 30% efficient times your heat input. Q2 will be Q1 minus whatever is your work done. Q4 will be the remaining work done. So are there any questions in this? If you can observe that previously the total heat rejection was around 6,298, but now it fell down to around 2,618. So this is because of the less efficiency. As more and as efficiency keeps on decreasing, what would happen is this Q2 is the heat rejected to the ambient. So basically, your work reduced for the same amount of supply. Since work is got reduced, your output is also get reduced. There are no questions, then we'll move on to the next problem. Yes. This problem is about a heat pump. So unlike a refrigerator where you aim to focus on where heat is rejected from, in a heat pump you focus on the other end of the Carnot cycle. So basically you focus on where the heat is rejected to. So this is used to maintain a temperature of 0 degrees Celsius in a refrigerator when it rejects the heat to the surroundings at 25 Celsius. If the heat removal rate from the refrigerator is 1440 kJ per minute, determine the COP of the machine and work input required. So for the first problem, so again just as usual, we just note down, convert everything from Celsius to Kelvin. So T1 is at 0 degrees Celsius. So Q1 is the heat removed from the refrigerator. Since T1 is refers to 0 Celsius, I will call that as Q1 just to be consistent with the units. So I'm just converting that into kilojoule per second. So what is the COP? How do I calculate COP now? If this is information is given, what is COP in terms of temperature? T1 is basically your source. So that is my output that I want divided by whatever is the input. Input is with respect to the work done. So that is T2 minus T1. So we just substitute the value. I just use a subscript here. This is for the case of refrigeration. Now, if it were a heat pump, so what would be my case? So in case of heat pump, the objective is to focus on the rejected one. So basically, instead of T1, it will be T2 by. Now, work done calculation straightforward. You know COP and you know the heat rejection rate. So what is the work done? The question asks, the next part is like, if the required input to run the pump is developed by a reversible engine, which receives heat at 380 Celsius and rejects heat to the atmosphere, then determine the overall COP of the system. So now this work, whatever is there, has to be supplied by a heat engine with a source temperature of 380 Celsius and a sink temperature of same as that of the previous one. So that is 25 degrees Celsius. So what would be the amount of heat generated in that case? Heat from the source that is required. So if I need the same amount of work, what would be the, we can just calculate the eta first. And since it is the same amount of work, the amount of heat required will be, let's say, roughly 2.2 kilowatt by 5.54. just to be use different units between heat and work. I'm using kilojoule per second. So this is the amount of heat that will be supplied, that you need to supply. So what is the COP in this case? The first case is clear. COP is T1 by T2 minus T1. So what is the COP now? How do I define COP now? So I want to consider, so there is a heat pump and there is a heat engine, both are there. So how do you define COP for the entire system? Maybe first you can think of as a refrigeration, and then we will convert that into heat pump, whichever way you feel convenient. So COP, efficiency, and all these are related to your output and input. So in terms of output and input, uh, how do I put this thing? So what is my output? What is my input in this case? The desired output is to maintain this removal rate from the refrigerator. So yeah, that is Q1, and my input is this amount of heat that I am supplying to the heat engine, right? So that will be 24 by around 5.89. But then if I were to calculate the other one, say for example, just as we said previously, let's say heat pump. If it were a heat pump, then we would focus on the heat rejected to the ambient. So what is the net heat rejected to the ambient in this case? So already we have a previous value. So if Q is the supply and work done is the same, so the rejected one value will be minus the same amount of work that we have to do. So this amount of heat is rejected to the ambient, and previously from the heat pump also we have certain amount of rejection. So in the previous case, what is the heat rejected? Yes, 26.2, and then we have here we have around 1.874. So the net heat rejected is 26.2 plus 1.874. This is the net rejected by whatever amount you have supplied. The supplied is this one over here, 4.074. So this is a COP of, if you consider it as a heat pump. If you consider it as a refrigerator, then it will be 5.8. So the basic idea is output by input. Whatever is your desired output divided by whatever is input that you are giving to meet that output. Are there any questions in this? Yes. The first one is a heat pump, right? So you have 0 degrees Celsius, 20 from zero. It is this 24 kilojoule per second is from 0 Celsius, and then work you are doing on the system. So zero, whatever heat is coming from 0 Celsius plus whatever work you are doing should be equal to the total amount of heat that you are rejecting to the ambient. That is how a reversed engine works. Yes, it is a work done is negative. Any other questions? We can move on to the next problem. So we have an ice plant that is working on a reverse Carnot cycle heat pump and produces around 15 tons of ice per day. The ice is formed from water at 0 Celsius, and the formed ice is maintained at 0 Celsius. The heat is rejected to the atmosphere at 25 Celsius. The heat pump used to run the ice plant is coupled to again a Carnot engine, which absorbs heat from a source maintained at 220 Celsius by burning a liquid fuel of 44,500 kilojoule per kg calorific value and rejects heat to the atmosphere. So the sink temperature is same both for the reverse Carnot cycle as well as the heat engine. Determine the power developed by the engine and the fuel consumed per hour. We'll assume that whatever heat is generated from the Carnot heat engine is completely given to the Carnot reverse Carnot cycle. So how do you calculate the power? by the engine. So what are all inputs are given? So if you just write the, okay, what is the desired, say for example, in the previous case, my desired value, desired objective is to the removal rate of the refrigerator. So what is the desired objective here? The desired objective is to maintain the ice at so and so temperature of 0 degrees Celsius. So what is the amount of heat that is required to be removed from the space so that ice will always be maintained at that temperature? So let's call it Q, since it is the reversed one. So basically heat pump. So let's call P, and it is rejected. So you have 15 tons of ice being produced. So 15 into 1000, 15 kilograms. And what latent heat is given as 334.5. And it says that 15 tons of ice is produced per 1 day. So we just convert it into our units. So 1 day is basically 24 times 60 times 60. So what is the COP in this case? You have the temperatures already, so I can directly write it. So just as you said before, so it is T1 by T1, T2 minus T1. So 273 is my refrigerated space divided by 25 is 298 minus 273. Once I have my CO, sorry, 10.92. Yeah. So you have COP, so you can, this is the amount of heat that needs to be rejected. So what is the amount of work done? Around 5.3 kilowatt. So the same amount of work has to be provided by the heat engine. So the efficiency of heat engine is already given. Like we can calculate the efficiency. We know the source and the sink temperature. So 1 minus sink temperature is same divided by your source temperature. It's 220 plus 273. Around zero point 0.4. So if W is amount of work, then the net amount of heat. So this is the amount of heat that needs to be supplied by the first one is done. The power developed by the engine should be around 5.3 kilowatt. The fuel consumed is first we calculated the net amount of heat that you require to supply. From this, you know the calorific value. So what is the amount of fuel that you have to burn? Is basically the Q divided by your calorific value. The calorific value is 44,500 kilojoule per kg. So this will give you in terms of kg per second. You can just convert it into any other unit. So maybe, yeah, maybe we'll just convert it into kg per hour. So what is the value you are getting? I think there are no questions in this problem. Yeah. Sorry, I didn't get it. Efficiency. The efficiency of the Carnot engine is operating between 220 Celsius and rejecting it to heat to the ambient. So it between 220 and 25. So efficiency is 1 minus your sink temperature by source temperature, right? Okay. And we move on to the next problem. So here it's again you have two Carnot engines, but then they are working in series. So what do you mean by series is like this is the first engine, and then you have another one, second heat engine, and this is the final sink. So this is heat engine 1, this is heat engine 2, this is my source is at say 550 Kelvin, and the sink is at 350 Kelvin. If both engines develop equal power, so it is given already that the amount of power that is generated from here, let's say W, is same for both the engines. So this heat engine also gives the same amount of power W. So what should be the temperature of, let's say here you have a sink. So maybe I'll put some another sink. This is, let's put it as T2. Let's say this is T1. Let's say it as T3. So what we are saying is we need to find the intermediate temperature here. T1 is given. So maybe I'll put this as T1. T1 is equal to 550 Kelvin and T3 is 350 Kelvin. What should be the intermediate temperature here? So that W will be same for both of them. So this should be again, maybe it can take a couple of minutes to solve. These are the basic equations. You can define the Carnot efficiency for the first heat engine, and you can define the Carnot efficiency for second heat engine, and then we have an energy balance for the first heat engine as Q2 is Q1 minus W. If you substitute this back, you get an equation like this, and get the relation between T1, T2, and T3. So what is the relation you are getting? So were you able to get this relation? Okay. So it's just a substitution. So we know T1 and T2 is 550 and 350. So the intermediate temperature is around 450 Kelvin. So if you need both the powers to be same from both the heat engines, then the intermediate temperature should be half of between the source and sink. If we didn't solve a problem, there is you can also have a similar problem in case of if you have a compressor, which we will do a little later. You can have two different compressors staged one after the other. You need to determine the intermediate pressure on a different criteria. So here the criteria both have the same work. In similar, you might have different criteria. Depending on the criteria, you decide what should be the intermediate pressure. We will take up the problem maybe once that compressor or source is start. Okay, we'll move on to the next problem. So here again we have a Carnot heat engine and a refrigerator, and both of them are connected in such a way that the Carnot engine will again drive the refrigerator, which absorbs heat from reservoir at temperature T2 and rejects heat to a reservoir at temperature T3. If T1 is given and T2 is also given, determine the temperature T3 such that the heat supplied to engine Q1 is equal to the heat absorbed by the refrigerator Q2. And once you do that, you can calculate the efficiency and CO. So if I were to draw it on diagram, just to put it as a schematic. So you have T2 as 300 Kelvin. You have a refrigerator, and then you have an unknown temperature T3 that you have to find. Similarly, there is a source. This is for the heat engine. The source temperature is 600 Kelvin. You have a heat engine. So there is a heat interaction from source to the heat engine, and heat engine will reject heat to the sink. Similarly, you will take heat from your refrigerated space, and then you will reject it to the same sink. There is a net work output by the heat engine that is used to drive the refrigerator. So this is the work done. Let's say this has Q2, this is Q1. You need to find this Q1 and Q2 now. So how do I calculate Q1 and Q2? Sorry, basically I need to relate them in such a way that you need to relate them in such a way that Q1 is equal to Q2. Then what is the temperature T3? Which temperature T3 will cause the Q1 to be equal to Q2? So that this is the same amount of work that is being, whatever is generated is used for the refrigerator. So we start, you always start with again your Carnot efficiency, and then you know this is a work done. So you know Q2, so that will give you Q3 here, or give it whatever name you want. Let's say this is Q3, and let's say this is Q4. So how do I relate it? Eta for the heat engine is W by Q1, and that is 1 minus your sink temperature by source temperature, T3 by T1. And similarly, you can do the same for the second one. COPS is your output. So what my output is Q2. My input is the work done that I am doing. So that will be T2 by T3 minus T2. So I know work is same for both of them. And Q1 is W by eta, and Q2 is W times COP. And we are saying Q1 equals to Q2, so which means eta times COP is 1. So if you substitute that, we have T1 minus T3 times T2 by T1 times T3 minus T2 equal to 1. So we know T1 and T2. So T1 is 600 Kelvin, T2 is 300 Kelvin. So if you substitute that, you can directly calculate T3. So what is the value of T3? So are you getting something like this? Yes. So previously we have what we have got is an arithmetic mean, and now what we ended up having is when you have this as a common thing, you ended up having an harmonic mean. If you just substitute the values, so 2 times 600 times 300. So we found the temperature T3, like the temperature of the sink. So now what is the efficiency of Carnot engine and COP of the Carnot refrigerator? Now you already know the T3, so you can substitute that back in the original equations to calculate eta and COP, so that is straightforward. So the second part is straightforward. So I don't think there are any queries in that. So just calculate T3, substitute and calculate. There are no questions. Then we can move on to the next problem. A heat pump working on a reverse Carnot cycle takes in energy from a reservoir maintained at 5 Celsius and delivers it to another reservoir where the temperature is 77 Celsius. The heat pump derives power for its operation from a reversible engine operating within the higher and lower temperatures of same 1077 and 77. For 100 kilojoule per kg of energy supplied to reservoir at 77, estimate energy taken from the reservoir at 1077. So this is also similar like the previous one, but here we have instead of having a common sink, here we have something else. So if you put in the schematic, so we have T2 as 350 Kelvin, then we have a heat pump H2, and this heat is getting rejected to space, that is T1 is T2 to T3. T3 is at 278 Kelvin, where the power is being supplied by this power, whatever to drive this heat pump, we need to supply power that is being given by your another engine, and that heat engine is getting energy from a different source, which is at around 1077 Celsius. One thousand seventy-seven is 350 Kelvin. This heat is getting supplied, and then it is getting rejected to the same thing. Whatever is the remaining work done, that will be done on the heat pump. So let's call this Q1, this is Q2, this is call this Q, this is Q3, and this is Q4. So what are we supposed to find in this problem? We are supposed to find the energy taken from this wire. We are supposed to find Q1. So how we, so which information is already provided to me? So what is this 100 kilojoule per kg? Yeah, temperatures are provided. So I have already written down the temperature T1, T2, T3. And then what is this 100 kilojoule per kg? So which of these is 100? Q1, Q2, Q3, Q4. Which one is it? So Q2 is energy supplied to the reservoir. Then what about Q4? Q4 is also being supplied to the same reservoir. So like, yeah. So what is 100 then? It's combination of both. So the total heat, like for 100, the total energy supplied to the reservoir is Q2 plus Q4. Both of this is getting supplied to the same reservoir. Yeah? So Q4 plus Q2 is your 100. So this is the information that is provided in the problem, and you are required to find Q1. So how do I do that? So how do I relate Q2 and Q1? So all we wanted to do now is, if you can relate Q2 with Q1, you'll basically, this Q2 will be replaced with Q1 and some terms, and you can relate Q4 with Q1, then this again will be replaced with Q1, and then eventually you'll have one equation in terms of Q1, so you can directly get Q1 from that. So how do I, yeah, yes, so we use again the same relation. So first the relation we can use is Q1 by T1 is Q2 by T2. We know T1 and T2, so you can directly replace Q2 as Q1 times T2 by T1. T2 is 350 by T1 is 1350. We have Q2 in terms of Q1. Now we need to relate Q4 in terms of Q1. So what is Q3? Sorry, what is Q4? In terms of, if we use the same relation as we have, so again we use Q4 by T4 is Q3 by T3. We know both, sorry, there is no T4, T4 equals to T2. And we also know that the amount of work done will be same for both of them. So Q4 minus Q3 should be equal to Q1 minus Q2. So we substitute all the equations in the below equation. So Q4 minus Q3 in terms of Q4 is Q4 times T3 by T2 should be equal to Q1 minus Q2. Q1 minus Q2 again in terms of Q1 we already have as 350 times Q1 by 1350. So now we get from these equations you can directly get Q4 in terms of Q1. So what is that value? You can just substitute Q4 into 1 minus T3 by T2. So what is Q4 in terms of Q1? Once I have Q4 as well as Q2 in terms of Q1, I can substitute in the original equation. So, okay, did you get the same value as this between Q4 and Q1? Sorry? Okay. Yes. Yeah. So you can substitute it back in the original equation and then tell me what is the final value of Q1. I got it around 25.906. But it's the same thing, right? You use the same equations. So you just replaced, you use this equation as well as Q4 in terms of Q1, Q2 in terms of Q1. Substitute them back in this. As long as, like, I think it's minor decimals, okay. I just use fractions, so you might have used decimals instead of fractions. There might be that. Yeah, you can check it later. So I think the problem is with the decimals one. You might have used decimals instead of fractions, so there will be a little difference. Move on to the next problem. So the next one is on how do you identify whether a given cycle is reversible or irreversible? So this impossible we have already discussed in last week. So how do you know it is impossible? You calculate the Carnot efficiency. The Carnot efficiency is the maximum efficiency that is possible. So if for the particular with the given values, if you get a higher efficiency, then that is impossible. Now in this week we have two additional things: a reversible versus irreversible. This is where your Clausius inequality comes into picture. You calculate the net entropy and then see if it is positive. If the efficiency is less than Carnot efficiency, then it is because of some irreversibilities. If the efficiency is equal to Carnot efficiency, then it is a reversible cycle. So all we have is three different cases. So we can have eta greater than eta Carnot. We can have less than, or we can have equal to. So the first one is a case of if it is greater than, then it is not possible. If it is less than, then there are some irreversibilities, or we'll just say reversible. If it is both are equal, then it is a reversible cycle. With this information, you can just calculate for the given values. Since the source and sink temperatures are given, we can directly calculate the Carnot efficiency. So maybe first I'll convert the temperatures. 563, and then the efficiency is and here we have the heat which is supplied, so which is Q1 is 300. We'll do it case by case. Case 1, Q2 is 215. So you have Q1. So what is the W? So W is around 85. So efficiency is that is around, sorry, so I'm getting it around 0.2. Yeah, so this efficiency 0.28 is less than 50%. So it is, and there are some irreversibilities in it. Now case 2, Q2 is 150. So what is the W in that case? Okay, I should have used consistent. So what is eta in this case? So it is 150 by 300, so that is 50%. So this eta is equal to Carnot efficiency, so the cycle is. Now case 3, you have 75 kilojoule per second, so Q2 is 75. So what is the work done? And what is efficiency? Which is greater than Carnot efficiency. So this is cycle is not possible. So suppose you want to use a Clausius inequality for each of these cases. So how do you use it? So for the case one, let's say, so sigma del q by t over the entire cycle. So that will be q1 by t1. Q1 is a heat supplied to the heat engine, so Q1 is positive. So and plus to the sink heat is getting out of the heat engine, so that will be a minus Q2 by T2. This summation should be negative. If it is negative, then the Clausius inequality is satisfied, and then so let us check if it is negative. Or if it is less than 0, then it is an irreversible process. If it is equal to 0, then it is a reversible process. If it is greater than 0, then it is not possible. So all you have to do is check this value. But if you see the relations, this eventually turns out like this will come out to be your efficiency. You can relate this, take the Q1 out, and then it will be in terms of, you can write this equation in terms of efficiency eventually. Like your efficiency is 1 minus T2 by T1. I don't, you can try this out later and see what are the results you are getting. I'm just putting it here so you can refer. If it is less than 0, then it is possible and reversible. And then there are other scenarios. If it is equal to 0, then it is reversible. And if it is greater than 0, then impossible. Then we can move on to the next problem. So here we have a steam power plant that is operating between a boiler temperature of 160 Celsius and a condenser temperature of 50. So again, this you can consider it as a heat engine. The water enters the boiler as saturated liquid and steam leaves the boiler as a saturated vapor. You need to verify the Clausius inequality for the cycle. The enthalpy of the water entering the boiler is given, and the steam inlet and outlet enthalpies are given. The condenser pressure is also given. So how do you solve this? So first step is always just converting the temperatures into the appropriate units. So Clausius inequality is again just as we have written before, Q1 by T1 minus Q2 by T2 should be less than or equal to 0. In case of reversible, it will be equal to 0, otherwise it will be less than 0. So in order to verify this, I know T1 and T2, I need to calculate Q1 and Q2. So how do I calculate Q1 and Q2? Okay, so basically you have one equation. So efficiency. So again, we are trying to see whether the Clausius inequality is satisfied or not. But the efficiency is the formula that you have is only for a reversible cycle. Like only if you have a reversible cycle, you can use that efficiency formula. So if you are using efficiency and calculating Q1, Q2, this one will eventually come out to be 0 because that is how you derive the equation for efficiency, right? Yeah. So any other way you can calculate Q1 and Q2? Yeah. So what are the enthalpies that are given? So the inlet of the boiler is given as 687 per kg. That is in the liquid state. Similarly, in the vapor state is given the outlet of the boiler, G2, or okay, it's not getting given as saturated vapor, so G2 is 2760. So with these two values, what is the value of Q1? Difference between the enthalpies, that is 2760 minus 687 kJ per kg. So that is the from the boiler side. So how do I calculate on the condenser side? Yeah, so you have the condenser pressure, and then so the condenser pressure PC is 0.124 bar. Yeah, just write it in bar. And then what else do I have? If you, the cycle is something like this: you have a boiler, you have a turbine, then a condenser, and then pump. This is like a typical steam engine cycle. So the inlet H is one is given, and then the outlet of the boiler is given, and the condenser pressure is given. So how do I calculate H3 and H4? So here, I'm not sure if so if you're already aware with isentropic expansion, so we usually assume that this expansion process in the turbine and inside a pump, the compression process, for typically you can assume it as an isentropic process. So all you have to do is for the state of the whatever is the state 2, you calculate the entropy from the steam table and see the same entropy value is maintained at the condenser pressure. For example, if you get the steam tables, so let's say if you want to calculate the isentropic process between two different pressures, in our case, the pressures are, what is the boiler pressure? So the saturated vapor is at 160 Celsius. So if you go to the temperature table, at 160 Celsius, the pressure is around 6.16 bar. So you are moving from 6 bar pressure to 0.12 bar. So if you look at 0.12 bar pressure, so it's around 0.1 bar. The temperature is this, and the entropy value is somewhere between these two. In the previous case, the entropy is around the entropy is 6.75. So all you have to do is to look up at we need a pressure of we need entropy of 6.75 at a pressure of 0.12 bar. So it will be somewhere in the two-phase region. So all you have to do is use the same entropy here and then calculate the vapor fraction from this and use that vapor fraction to calculate the enthalpy. Is that clear? Yes. We are taking entropy to be same. So S and then you will calculate the enthalpy. So S2 equal to S3 is what we are using. Sorry, quality. Huh. So if you put S3 here, you can calculate quality from SF and ST. And then we also have HF and HG. So once you get quality, you can use that to calculate the enthalpy. Okay. So I'm not going through steam tables again. So I'm directly writing the values here. So once you do that, the value of H3 is around 2160 kilojoule per kg. Maybe I'll just write down here. So whoever refers this after the lecture, assuming isentropic process, that is S2 equals to S3, calculate quality, and from there we calculate H3. And the final state is from H3 to output of the condenser. So how do you calculate that? So we're assuming that whatever is going into the pump is in say saturated state at the same pressure. So it will be around the pressure is around 0.124 bar. It is somewhere in between these two. So the enthalpy will be somewhere in between these two. So you just do a linear interpolation between 0.1 and 0.2. Then between 191 and 251. So the value comes to around 209. So once you have H3 and H4, calculation of Q2 is straightforward. Q2 is basically H3 minus H4. So once Q1 and Q2 are calculated, then the process is all, you already know what the process is for process equality. So all we need to do is just check this Q1 by T1. Q1 is 2073 divided by T1 is 433 minus Q2 is 1951 divided by T2 is 323. What is the value you're getting? I'm getting it around minus 1.252, which is negative. Since it is negative, then the process inequality is satisfied. So if you would have used, so now comes the next question. So we assume that this process is an isentropic process. So then how come this came out to be negative? So, as we discussed before, if it is equal to 0, then it is a reversible one. And if it is less than 0, then there are some irreversibilities. So what do you think are the irreversibilities here? I think, okay, these are not yet discussed in the lecture videos. Okay, we'll discuss this in the next week. So what are the other causes of what are the different types of irreversibilities that can happen? So maybe we'll discuss it. Yeah. Sorry. Yeah, friction is there. So where do you think we accounted for friction in the calculations that we have done now? Throttling is not like throttling is used in refrigeration cycle. So in this cycle there is no throttling. So you have a boiler, turbine, condenser, and a pump. In refrigeration cycle you have a throttle. So there are different kinds of irreversibilities. One is that you mentioned is friction, and other things are heat transfer happening at a finite temperature difference is another source of irreversibility. So like in the boiler and the condenser that we are referring here, if how is the heat supplied to the power plant? Like how is heat supplied in the boiler? Maybe we'll discuss in the next week the different kinds of maybe I'll take up some problem and then we'll discuss what are the different kinds of reversibilities that can happen and why is it an irreversibility and how this gets reduced. For now, it should be clear that how to check whether this clause is inequality. If that is clear, then that is done. That is the aim of this problem. Yes. Yes. So you have, for example, the pressure is around 0.1 bar. Once you calculate the quality, you can use HF and HG to calculate that, right? So HF plus quality times the HFG should give you the enthalpy. Okay. Yes. This HFG is basically HG minus HF. Yeah. So moving on to the last problem. This is also very similar one like before, but here I've already given the values of enthalpies directly. So all you need to just calculate verify the clauses inequality. So it is again straightforward. You just convert the temperatures to Kelvin first. Since Q1 and Q2 are straightforward here. So what is the Q1 here? Q1 is a heat supplied. So that is H2 minus H1. And Q2 is for the condenser. So condenser rejects the heat. So it will be H3 minus H4. Now you can directly check the cross equality. So Q1 by T1 minus Q2 by T2. And minus 1.158, which is negative. So again, this is verified. So both these problems are again the same, just that the values are here given directly. All you need to know is which difference you need to take to calculate the value of Q. That's the only thing. So I think there are no questions in this. Yeah, these are the questions I have for this week. If you have any doubts, then we can discuss. Otherwise, we can call it a day. Yes. Okay. This one. Okay. Hmm. So cool. Just check and let me know. Hmm. Oh, okay. The calculation is W is 1 kilowatt, 0.3, right? Thank I'll update this. Okay. Yeah, thanks for the correction. If there are no questions, then we can end the session for this week. Yeah. Thank you for joining. We'll meet next week.